Welcome to this Forge College Explainer. Let's just jump right in. Today, we're unrolling the blueprints for building a modular contract skeleton. If you've been sticking with us through the Solidity from Zero track, you know we're picking up exactly where we left off in exploring abstract contracts. So let's get our hands dirty and see how all these pieces actually fit together.
So, quick question. Are you ready to build a smart contract Frankenstein? Okay, a good one, obviously. One that doesn't go chasing villagers with pitchforks. Now that we've survived the underlying theory of abstract contracts, it's time to take those loose, disconnected parts and assemble a beautifully modular skeleton. Think of it like a base mechanical chassis. It works perfectly and securely all on its own, but it's specifically designed to let you safely snap on custom parts later on without having to tear the whole machine apart. Honestly, it's a little piece of engineering magic when it all comes together.
Here's our agenda for today's blueprint. 1. Why build a skeleton? 2. Step 1. The interface. 3. Step 2. Abstract contracts. 4. Step 3. Concrete implementation. 5. Passing the smoke test. And 6. Modular next steps. Let's get to it.
Starting with Section 1. Why build a skeleton?
To really get why we do this, we have to look at the huge problem with monolithic contracts. I mean, if you try to bolt new features directly onto a massive single-file contract, you risk breaking audited secure code. It's incredibly dangerous. So we build skeletons to achieve a true separation of concerns. And the magic mechanism that makes this massive structured reuse possible? It's called the extension point. Basically, an extension point is a specific, protected internal hook in an abstract contract where derived contracts can securely plug in custom logic. Think of it like a built-in, patent-pending mechanical socket. By using this socket, new code just smoothly plugs right in. It's highly efficient for us developers because the core engine remains completely untouched and, most importantly, secure.
Moving on to Section 2, which covers Step 1 of our build, the interface.
Our first crucial file is iWidget.sol, which represents our external capabilities. Step 1 on our assembly line focuses strictly on the buttons and dials the user actually interacts with. Our interface is kept entirely clean and contains absolutely zero logic. Seriously, if you look inside this file, you won't see a single curly brace executing code. None. It only holds the external function signatures and events that define exactly how callers interact with our contract. Think of it as a pure contract of communication. It's the dashboard of the car, with absolutely zero knowledge of how the engine actually works under the hood.
Section 3. Step 2 of the build. Abstract contracts.
Now we have abstract-widget.sol, where our protected state and hooks live. This right here is where we wire up the actual engine blocks sitting just behind those external dashboard buttons. Our abstract contract steps in and implements that interface we literally just looked at. It sets up protected state, things like assigning ownership and handling strict access control checks. But most importantly, it delegates the heavy lifting behavior to an internal hook called execute action. In Solidity, we explicitly mark this function with the virtual keyword. This is that extension point we defined earlier. It provides all the shared security checks up front, but leaves the specific action deliberately blank for derived contracts to fill in later on.
Seeing these side by side really highlights the complete separation of concerns. On the left side, iWidget.sol, your pure external declarations, live safely on their own. On the right side, abstract-widget.sol, your internal engine, state, and security checks live securely isolated. By splitting them up into these two distinct blueprints, your external users and front-end applications only ever need to know about the interface. Meanwhile, your smart contract developers can safely tinker with the heavy engine logic inside the abstract contract. It's super clean.
Next up is Section 4, Step 3, Concrete Implementation, or as I like to call it, the custom paint job.
Enter widgetimp.sol, the custom paint job and the actual fuel in the tank. The derived contract, our concrete implementation, inherits the abstract base and finally gives real, executable logic to that execute action extension point we left open. Because the abstract contract marked that function as virtual, our derived contract uses the override keyword to officially plug into that socket. It successfully honors the interface, it utilizes all of the abstract contract's built-in security checks, and it provides the final missing piece of the puzzle to make the entire contract fully functional and ready to deploy.
Okay, let's summarize this entire architecture, because honestly, understanding this exact three-file layout is absolutely everything. It forms the ultimate scaffold for our modular engineering blueprint. First, iWidget.sol is your external interface, containing only signatures and events. Second,
Abstract widget.sol is your protected state, your shared security logic, and those crucial internal virtual hooks. And finally, widget implement.sol is your concrete implementation, demonstrating the actual extension logic. This specific trifecta right here is literally the absolute gold standard for contract modularity in the Web3 industry.
Which brings us to Section 5, passing the smoke test. It's time to turn the key.
Passing the smoke test to see if our code breathes fire is a strict 4-step process. First up, compile. The compiler will absolutely yell at you, and honestly, rightfully so, if your concrete contract forgot to implement a required abstract function or if there's an interface mismatch. Second, once it compiles cleanly, deploy it locally to your test environment. Third, trigger that external function we mapped out. And fourth, verify that the abstract hook actually updated your underlying state properly. If you can perform these 4 steps without the Ethereum virtual machine catching fire, your Frankenstein skeleton is officially alive. No way around it, that's a great feeling.
But wait, before you ship this architectural masterpiece to production, we really need to talk about NatSpec documentation rules. Before you finalize your blueprints, ensure every single extension point is documented with crisp, clear NatSpec comments. You need to document the expected behavior and explicitly explain the extension points. You also absolutely must note what the derived contract's responsibilities are and clearly define any invariants. Now, invariants are the fundamental underlying rules of your contract that must never, ever change, no matter what custom module gets plugged in later on. Why do we do this? So future maintainers know exactly how to interact with your skeleton and don't accidentally turn your helpful modular robot into a very dangerous monster.
Section 6. Modular next steps. Let's talk about future upgrades. Now that we have a fully functional, rigorously tested, and well-documented chassis, we are perfectly positioned for those upgrades. In the very next lesson in our track, Principles of Contract Modularity, we're going to use this exact skeleton as our base artifact. We'll start snapping in multiple interchangeable plugin modules. Just imagine dropping a complex staking module in today and then effortlessly swapping it for a decentralized voting module tomorrow. We'll be creating highly adaptable smart contracts without ever having to touch or rewrite that core secure engine.
So the final question I want to leave you with is this. If every smart contract becomes a modular, swappable skeleton, will we ever really need to write complex contracts from scratch again? Or will Web3 development just become a game of snapping together the perfect Lego blocks? Think about it. Thank you so much for exploring this with us today. This explainer was made by Forge College. Be sure to visit forge.college to dive deeper into smart contract architecture and explore tons of other fascinating Web3 topics. Keep building, and we'll see you next time.